Okay, chapter 5. Work is the result of a force applied times the displacement traveled in the direction of the applied force. Any movement not in the direction of the applied force is disregarded. Uh, so if I'm pushing on something this way and it moves this way or that way, okay, because the force is applied horizontally, the only work I'm concerned about is the horizontal work done. If it tends to go up a ramp, the elevation is irrelevant. It's only in the direction it is. Likewise, if I'm on an elevation and I'm pushing up an incline, then it's parallel to the incline. If you do work against gravity, then we're only concerned about the elevation, not the horizontal distance, because ramps are basically simple machines that make jobs easier. All right, because the longer the ramp, the less force you need. All right, to do the job. Work is force times distance, and work is measured in joules. Now, work is a form of energy, and energy is a scalar quantity. And for that reason, it's not a vector. Okay, it does not have direction, but the direction is important in determining the actual work. Like I said, the work has to be done in the direction it's moving. Any other types of movement we disregard. Okay, potential energy is thought of as stored energy within a physical system. It's called potential energy because it has the potential to be converted into other forms of energy, such as kinetic energy and work. The SI unit for potential energy is also joule, same as work, and it is also a scalar quantity. Okay. Gravitational potential energy is mass times gravity times height, and the height is relative to the system you're looking at. So if you're lifting things from the floor, then 0 is the floor. If you're lifting things from the desk, then 0 is the desktop. Okay, so you have to take that into consideration. So the factors that affect an object's gravitational potential energy are its relative height to a reference point, its mass, and the strength of the gravitational field in it. Now, G on the surface of the Earth is 9.81 meters per second squared. Okay, but if we went to Denver, Colorado, gravity would be like 9.79 meters per second squared. All right, because it's farther away from the center of the Earth, gravity's pulling on it less. It says, thus, a book lying on a table has less gravitational potential energy than the same book on top of a tall cupboard, and less gravitational potential energy than a heavier book lying on the same table. An object at a certain height above the moon's surface has less gravitational potential energy than at the same height on Earth because the moon's gravity is weaker. The gravity on the moon is 1/6 of the Earth. Okay. It doesn't have 0. If it didn't have 0, the moon wouldn't be around. It would just start falling apart. Okay. So the gravitational force keeps the planets in orbit around the sun. Elastic potential energy is the potential energy of an elastic object, mousetrap, spring, anything that's like under a tension like that. And we use the formula potential energy of a spring equals 1/2 kx squared, where k is the spring constant. The higher the number, the stronger the spring is. Okay, like a clicky pen or a pencil, the spring is very, very easily to maneuver. That has a very low k, but a spring on an automobile, all right, that helps it keep the tire on the ground, that is a very high one. Okay, very hard to compress that. Chemical potential energy is a form of potential energy related to the structural arrangement of atoms or molecules. This arrangement may be the result of chemical bonds within a molecule or otherwise. So if you took chemistry and you're using things from the left and the right-hand side of the periodic table, when they put together, large amounts of heat are released or absorbed based on the process used. This is where that comes into play. Electrical potential energy. The electrostatic potential energy is the energy of an electrically charged particle at rest in an electric field. It's defined as the work that must be done to move it from an infinite distance away to its present location in the absence of any non-electrical forces on the object. The energy is non-zero if there's another electrically charged object nearby. We're not even really going to go into this. This is physics 2, okay? Electric potential energy, but I just showing it there that you have it, okay? Electrodynamic potential energy is simply magnetic energy. Okay, same thing. Chapter 2 or physics 2. Okay, so I won't go into that either. Nuclear, also physics 2. In nuclear potential energy, is potential energy particles inside an atomic nucleus from which are indeed electrically charged. Okay, so if you think of the nucleus of an atom, it has protons and neutrons in it. All right, those protons are both positively charged. They want to get away from each other, but the nuclear forces that hold it together is what we're talking about on that. Okay, and then there's a thing called weak nuclear force. That's just radioactive decay. Okay, so that's that. So in this chapter, I'm introducing a whole bunch of different types of energies, so you're just familiar with the terms. But we're mostly going to be looking at work, potential energy, kinetic energy, and potential energy of a spring. That's what we're looking at this year. Next year, the other stuff, you do formulas and stuff for that. Thermal's cool. I like this stuff. The thermal energy of an object is simply the sum of the kinetic energies of the particles making it up, plus the potential energies of their displacements from their equilibrium position as they oscillate or move around them. In the case of an ideal gas, there's no potential energy due to interactions of particles, but kinetic energy may include a rotational part too, if rotational levels are excited at a given temperature T. Now, thermal potential energy is basically science of like solar updraft towers, fireplaces, different things like that, where you have a hot source and hot air rises. As the hot air rises, and what it does is it starts to then spin turbines and stuff. Okay, like here's the link to the solar updraft tower. All right, so here's the picture here. Oops. All right, so basically what happens is the sun beats down on these collectors and heats up all the air down here. As the hot air rises, it turns the turbines and generates a massive amount of electricity. And then at night, the opposite happens. It starts to cool down, and then it turns the other way, okay? And then this is a picture of a solar updraft tower over a fireplace, okay? So what you have here is this little propeller spins when you light a fire in the fireplace, which then causes it to turn, and then you hook up the gears and you can run machinery like a block to crush flour or something like that. Probably wouldn't be flour because flour would be explosive if they were crushing it next to a fireplace, but they definitely could use it for other things, okay? And then this is a picture of a solar updraft tower. I think this is in I actually saw one down in the Las Vegas area. It was really impressive. But you can see basically it's like a plexiglass on the top, and then it heats up the ground. The ground re-radiates it, and that heat then has no place to go but up the chimney. So as it all rushes in there, it's like a wind tunnel of just hot air going up there. Okay. All right, let's go back to it. Dink. There we go. Yes. All right, kinetic energy is called energy in motion. Its formula is 1/2 mass times velocity squared. The faster the object moves, its kinetic energy increases by the square. All right, that's very important because people screw this up all the time. So if you double the speed, you quadruple the kinetic energy. If you triple the speed, 9 times as great because it's squared. All right. Conservation of energy. Energy can change without loss or gain. For instance, take the scenario of a girl shooting archery, right? Girl has a bow. The amount of work used to pull back that arrow, okay, is how much potential energy that bow now has. When she releases the arrow, all of that potential energy is converted into kinetic energy, and then it leaves with the arrow, okay? If you know the mass of the arrow, you can calculate how fast that arrow is going to come out of the bow, assuming that there's no loss due to friction or heat or anything else, okay? Power is how fast you do work. So it's work divided by time. And a joule per second is a watt. Okay. The faster you do something, the more power is produced. Think about engines, all right, in a car, all right. Uh, they're usually measured like in horsepower or kilowatts, okay. The bigger the engine, technically, the faster it could probably accelerate, okay. All right, Hooke's law. This is for a spring. If you have a spring hanging and you place a weight on it, it'll stretch. If you place another weight on it, it'll stretch more. And if you were to graph of force versus stretch, the slope would be K, which is your spring constant. As long as you don't put enough mass on it that'll actually deform the spring, it will follow this rule. Okay. Spring scales. All right. Like I'm a big fisherman. I have one of those hooks that you put in your fish's mouth and you pull it up. How does it tell you what the weight is of the fish? It's based on this formula. Okay. Because F would be the weight. Right. And then finally, the roller coaster. That is the most fun part of energy conservation. Why is the first hill the biggest? Well, it has to get all that energy. And then as it goes down, the potential energy at the top gets converted into kinetic energy as it goes down. And then as it starts to go back up, it converts back into potential energy, then back into kinetic energy. Eventually, it's losing some energy due to friction and the wheels and the air friction and everything else. So you have to make sure that first hill is big enough, okay? And it's neat, all right? And that is it for this part.